Hi, I'm Shih-Hsuan. I'm here to talk about the feature curves and surfaces for the analysis of 3D asymmetry tensor fields. This is joint work with Yue Zhang, He Ye, and Yujun Zhang. 3D asymmetry tensor fields have many applications, such as the stress tensor fields in solid mechanics and the velocity gradient tensor fields in fluid dynamics. These tensor fields encode fundamental behaviors such as rotation and deformation. While these types of motions can be understood by visualizing the vector field, tensor field visualization provides a more direct visual representation. Existing topology-based tensor field visualization has focused on symmetric tensor fields. However, since asymmetric tensors can have complex eigenvalues, the features are not well preserved by the symmetric part of the tensor fields. Second, researchers have attempted to understand 3D asymmetric tensor fields by performing 2D analysis for the projection of the tensor field on surfaces. Unfortunately, where the projected tensor have complex eigenvalues, does not usually coincide with the complex domain of the original 3D tensor fields. Lastly, the tensor field can be analyzed locally with glyph representations. This method highlights a fundamental need to perform topological analysis and visualization directly on 3D asymmetric tensor field. Therefore, we introduce the feature curves and surfaces for 3D asymmetric tensor fields, as shown here for the velocity gradient tensor field of the Lorentz attractor. A 3D asymmetric tensor can be decomposed into a multiple of the identity matrix and a traceless tensor. This traceless tensor has the same set of eigenvectors as the original tensor. Therefore, we begin with this analysis of 3D traceless asymmetric tensors. Here we show the real Schur forms of 3D traceless asymmetric tensors in the real domain and the complex domain. In the real domain, the diagonal elements are the three real eigenvalues of the tensor. In the complex domain, the 2x2 block of the Schur form represent the complex conjugate eigenvalues, and the last element is the real eigenvalue. Furthermore, the subblock also corresponds to dual eigenvectors of the tensor. The boundary between the real and complex domain consists of tensors with zero discriminant. We refer such a tensor at the boundary as the degenerate tensor. A degenerate tensor has at least two repeated eigenvalues as pointed out by its Schur form. And the degenerate tensors form surfaces which we refer as the degenerate surfaces. On the right, we show the shear 4 patterns of degenerate tensors by projecting the tensors onto the planes corresponding to the subblock of the shear form. Moreover, when A of the shear form is 0, all three eigenvalues of the tensor are 0. We refer such a tensor as a triple degenerate tensor. Unlike 3D symmetric tensor fields, the triple degenerate tensors for asymmetric tensor fields are structurally stable and form curves. Next, in the real domain, we distinguish a tensor into linear, planar, or neutral tensor by its median eigenvalue. In addition, a linear and planar tensor has the dominant eigenvalues as the major and minor eigenvalue, respectively. Based on these categories, we can classify degenerate tensors as being linear, planar, and neutral. Note, neutral degenerate tensors are actually triple degenerate tensors with all zero eigenvalues. Furthermore, we define the real neutral tensors which have the zero determinant. These real neutral tensors have a saddle for pattern and form surfaces. We also extend the real neutral tensor to the complex neutral tensor which forms surfaces as well. Note on the right the projection of a complex neutral tensor onto the plane spanned by dual eigenvectors is an elliptical flow pattern. Next, we analyze a 3D traceless tensor with the decomposition into its symmetric part S and antisymmetric part R. Unlike 2D tensors, where the strength of R is less than the strength of S, a 3D tensor can be in the compressed domain. Therefore, we define the inner and outer compressed domain for 3D asymmetric tensor fields, which can also represent the rotation dominant and shearing dominant regions. Then we define the balanced tensors where the strengths of R and S are equal. These balanced tensors have the real shear form where C squared equals to A squared plus A times B plus B squared. Note while A and B are 0, the tensor is also triple degenerate. Furthermore, the balanced tensors form surfaces which can be characterized with the minor of the tensor. The surfaces can also be separated into linear and planar balanced surfaces. To understand the eigenvector behaviors in the different domains, we trace a dominant hyperstring line and employ the metaphor in which the hyperstring line is a stem of a plant. Along the hyperstring line, the other eigenvectors in the real domain are represented as thrones, and the dual eigenvectors in compressed domain as leaves. When crossing the degenerate surface, the hyperstring line continuously changes from the dominant eigenvalues in the real domain to the real eigenvalues in the compressed domain. Furthermore, the other two eigenvalues in the real domain converge at the degenerate surface and morph into the dual eigenvectors in the compressed domain. At the triple degenerate curves, all three eigenvectors from the real domain and the real eigenvector from the compressed domain converge to the only eigenvector. Since the dominant eigenvalue of the real neutral tensor is not well defined, the dominant hyperstring line is not continuous while crossing the real neutral surface. Next, a tensor mode is an invariant for the tensor fields and intricately connected to the topology of the fields. We define the mode for 3D asymmetric tensors with the mu motivated by the formula for the eigenvalues of the tensor. Note the spatial tensors that we have defined earlier have unique tensor modes. Therefore, the tensor mode allows us to construct a model for all 3D asymmetric tensors, which we refer as the eigenvalue space. We first consider the set of all traceless tensors, which we map to the boundary of a hexagon made of the spatial tensors. Note the center of the hexagon corresponds to the triple degenerate tensor. In this model, the three pairs of the boundary from the top to the bottom represent the tensors in the real domain, outer compressed domain, and inner compressed domain. Moreover, the linear and planar tensors are separated into the left and right of the hexagon. To generalize the eigenvalue space for 3D asymmetric tensors, we define the notion of isotropicity as the eta. And we add to our eigenvalue space two additional spatial tensors, isotropicity of 1 and the -1. The eigenvalue space becomes a double hexagonal cone and a line segment in the middle. We then introduce non-topological feature surfaces for the analysis, such as the magnitude surfaces and isotropicity surfaces. We extract the feature surfaces with the Apache's method. However, many of the feature surfaces are quadratic surfaces, such as the magnitude surfaces, isotropicity surfaces, and balance surfaces. Observing that a quadratic surface is either an ellipsoid, a single-sheet hyperboloid, or a double-sheet hyperboloid, we propose a quadratic surface extraction at any given accuracy. We first extract the intersection of the surfaces with the tetrahedron and map the intersection curves to the parameter space which bound regions. Then we perform the de Morgan triangulation with the boundaries as the constraints. and map the points back to the XYZ space along with their connectivity, which gives our triangulated surfaces. For triple degenerate curves, we first find the balanced surfaces with the quadratic method, and then extract the zeroth level set of the determinant on the surfaces with the apertures method. We apply our analysis to solid mechanics and fluid dynamic datasets. Twisting motions acting on material is important to understanding the solid mechanics. We simulate a twisting of a block and visualize the features in the stress tensor fields for two different stages. The Cauchy stress tensor field, which is symmetric, shows little difference in the degenerate curves for the two stages. The PK1 stress tensor field, which is asymmetric, clearly shows the difference of the degenerate surfaces. Both the PK1 stress and Cauchy stress can provide important insights. Consequently, visualizing both types of tensor fields and understanding the connection between their structures can provide a more comprehensive analysis. Next, we visualize the feature curves and surfaces for the velocity gradient tensor field of the Rayleigh-Bernard flow. We run into the cell which shows the transition of the regions separated by feature surfaces. This helps to identify regions of stretching and compression as well as the rotation dominant space for the analysis of the underlying physics. In this ABC flow, we also visualize the features of the velocity gradient tensor field. We notice that there is a one-by-one correspondence between the set of triple degenerate curves and the 6 principal vortices of the ABC flow. We also trace our hyperstring line from the center of the cell that shows not only the eigenvector field but also the other eigenvectors or dual eigenvectors. Due to the periodicity condition, once the hyperstring line reaches the face, it will resume from the same point on the opposite face. Moreover, we observe that the vortex co-lines are inside the compressed domains and reside in the rotation dominant domains and crossed by the balanced surfaces. Also, the lines can be separated into linear and planar regions by the compressed neutral surfaces. These features can be potential of bringing additional insights for understanding the fluid dynamics. In conclusion, at the core of our analysis is the definition of tensor mode, which gives our feature curves and surfaces and lead to an eigenvalue space for 3D asymmetric tensors. The feature curves and surfaces state their topological significance, such as the triple degenerate curves are the spine of all mode surfaces, and balanced surfaces are the boundaries of the inner and outer compressed domains. To enable a holistic view of the eigenvectors and dual eigenvectors, we also visualize an augmented hyperstring line with the tree-based manifold. Lastly, we provide an algorithm to extract quadratic surfaces efficiently and quickly. In the future, we wish to investigate a more robust extraction of all the feature surfaces than the apertures method. We appreciate our reviewers, Avery, Yichuan, and National Science Foundation. Thank you for your attention.